In this video, we are going to look at the Science Paper 2 for the year 2017. And, we are just going to focus on Section B, and we are going to consider this one as Part 2 for this paper. And we'll have question 1 from Section B. The diagram below shows the cooling curve for a liquid. So we are dealing with a liquid. Now, whenever we are dealing with a liquid, first we need to look at the change of state of matter that will be associated with this cooling curve. So to move from liquid into a solid, then the change of state of matter must be freezing. If not freezing, we can use the word solidification. So that is what our focus is. Then we also have to look at the segments that we have. So we have 3 segments: segment 1, segment 2, segment 3, or if want, we can just use the word phase. We have 3 phases that we have here. Now, the first one, the first landing, which is point A, this is a liquid state. Why do we say it's a liquid? Because this cooling curve is for a liquid. So we are starting from a liquid, then going into a solid state. Now, whenever the substance is cooling, it means that the temperature is reducing, or we are removing the heat from that substance. Now, at point B, at this point, the temperature at this point, point B, is a temperature at which the freezing is taking place. So the liquid here starts to freeze. So we don't have the number. But let's just assume that we have a very low temperature, because for a liquid like water to freeze, the temperature must be very low. Now, the point B, this point B here, it shows the initial. So this is the initial point of freezing. So the initial, it means, is where the freezing is starting. Then our point C, we can consider this one as our final point of freezing, meaning the freezing is now done, the substance is completely a solid. So we have the freezing point here. Then the segment from B to C, this or region here indicates the process of freezing. Now, under or during the process of freezing, we are expecting to have 2 states of matter. So we are going to have part of a liquid, then also part of what? A solid. Then by point C, we have a completely solid. So this is a solid. Then even at D, this is a solid that we have here. Now, based on what we've discussed, let's look at the first question. Question A, in what state of matter is the substance in area A? So we have liquid as our final answer for this one. Then B, what name is given to the point labeled B? So the point labeled B, this one will be called a freezing point. It's a freezing point because it is indicating the process of freezing. Then in what states of matter is a substance between points B and C? We said we are going to have 2 states of matter. So we have solid and liquid. We move on to question D. Explain the reason why the thermometer reading remained constant between points B and C. So under point B and C is where the process of freezing is taking place. So during the process of freezing condensation, then the reading on the thermometer stops. It stops to do. Then explain the reason why the thermometer reading remained constant. So we'll say because the energy. So because the energy is used to bring the particles closer. Because whenever we want to change the substance from a liquid into a solid, if you look at the arrangement of particles in a liquid, there are more spaces compared to the arrangement of particles in a solid. So for us to change from a liquid into a gas, we just have to bring the particles closer so that they become closely packed. Immediately their particles are closer to each other, Then we have the change of state of matter. Okay, so we go to question E. Explain what happens during cooling in relation to the heat content of the substance. So, as we said, whenever we are cooling, heat is what? Removed. So, heat content is that. So, just say the heat content of a substance. So, reduces. That's what we can summarize. We move on to question B2. When a cesium metal is reacted with water, there is a rise in temperature. So whenever we have a rise in temperature, we are dealing with exothermic reaction. Why do we say exothermic reaction? Because this is same as heat is given out. That's why we have a rise in temperature. Now, if we compare this one to the previous question under cooling curve, that is also exothermic reaction, because also heat is given out. So during cooling, heat is given out. Heat is absorbed. So that is endothermic. But for this one also, it is an exothermic reaction because there is a rise in temperature. Now, question A1, how would you detect the rise in temperature? So for this one, we can just measure by using thermometer. So we'll say by using a laboratory thermometer, since this is done in the lab. Then what type of reactions takes place? We've answered that one. This is exothermic reaction. So remember, exo means given, I mean out. So we'll consider exo as out. Then thermic, it is coming from the word thermo. It has to do with the heat energy. So heat is given out. That is exothermic reaction. Then Roman number 3, give a reason for your answer in A to above. So we'll say because heat is given out. So that is what we can see. Then from question B, potassium is found in the same group of the periodic table as cesium. Compare the reaction of the two metals with water. So if you look at the arrangement of these metals in group 1, the first one is lithium. Then the second one we have sodium. Then we have potassium, we have rubidium, Rb. Then after rubidium, we have the cesium, which is Cs. Now, the group 1 elements are the most elements that we have on the periodic table. Now, even if these elements are considered to be the most reactive, there are those that are more reactive than the other within the same group, which is group 1. So what you do for group 1 elements, you just have to know that if you move down the group, then their reactivity increases. So the metal element below is more reactive than the metals or elements above. That is according to the trend under group 1. So if you look at the position of cesium and potassium, cesium is somewhere here. It's below that potassium is here. So cesium is more reactive than potassium. So the reaction, for example, of cesium with water will be more vigorously compared to the reaction of potassium with water. So that's what we are going to say. Because we are told B1, compare the reaction of the two metals with water. So we'll say the reaction of cesium, or just use symbol, cesium with water, is more, we'll say, is more violently than the reaction of potassium with water. Then Roman number 2, we have given a reason for your answer in B1 above. So say because cesium CS is more reactive than potassium. So according to the trend of group 1 elements. Now we move on to question 3. Beryllium burns in fluorine to form a white solid, beryllium fluoride. Name the type of bonding in beryllium fluoride. So first we need to look at the nature of metals that we are dealing with. So beryllium is coming from group 2 with the symbol Be. Then the mass number is 9, the atomic number is 4. So the valency will give us 2,2, which is there are 2 electrons in the outermost shell. So this is a metal. Then if you look at the fluorine, this one is coming from group 7 with the mass number of 19, then the atomic number of 9. So if we look at the electronic configuration, this will give us 2,7. This is a non-metal. So we are dealing with a bond between a metal and a non-metal. So whenever we have such compound made up of a metal and a non-metal, we are dealing with ionic bonding. Now we go to question B. In the space below, draw a dot and cross diagram to show the bonding in beryllium fluoride. Show all the electrons. Now first we need to look at let me first draw the atomic structure of beryllium. So beryllium, we are saying we have B. So we are going to have first shell and the second shell, since we are told to show all the electrons. Remember, according to the configuration, the first shell will occupy 2 electrons. Then the outermost shell will occupy 2 electrons. So for beryllium to be stable, it needs to lose 2 electrons. So these 2 outer or valence electrons must be given out for this atom to attain stability. Now for fluorine, let's look at the atomic structure. So under fluorine, we know that the first shell we put 2 electrons, then the outermost shell must have 7 electrons. Now the second shell is always occupied with 7 electrons. Now what happens in a case where the metal, the one giving is giving 2 electrons, but the one receiving needs only 1 electron? So what happens to this extra electron? So in this case, the fluorine atom must maybe let me borrow a term like must call another fluorine atom so that they can receive these 2 electrons. Because for beryllium to be stable, it doesn't matter how many electrons the other nonmetal is receiving. For it, if it is giving out 3, then it has to give 3. So since one atom of fluorine is not capable of getting the 2 electrons, then we need 2 atoms of fluorine atom so that they can share the 2 electrons that must be given out. So in a case like this, so if you are able to understand this point up to here, you understand the importance of valence. Let me show you the importance of valence. Like for example, we have beryllium valence 2 since it's coming from group 2. Then fluorine, which is F, is valence 1. So if we interchange, then we are going to have beryllium fluoride with this chemical formula. So I'm sure by now you understand what it means by this subscript 2. So it means we need 2 atoms of fluorine to get the 2 electrons that are coming from beryllium. So that's a point. Then we can now finish our structure. So for beryllium, we just write the first shell since the outermost shell, we'll not put that one into consideration. The electrons are given out. So we have first shell, second shell, first shell, second shell, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 plus the one that was received. Then we do the same. So we have now our beryllium fluoride. So since the total number of electrons that were received by these two atoms of fluorine were 2, so we put -2 here. Then since here it was 2 given out, so we put 2. So this is our ionic bonding. Then question C, suggests any 2 physical properties of compounds that have similar bonding as beryllium fluorides. This same as giving properties of ionic compounds. So the first one, we can say conduct electricity when in molten state. The second one, have high boiling and melting point. Right, so this is what we can give, though there are so many properties, so it depends on the one that you'll be able to remember. Okay, we move on to question 4. A learner wanted to obtain clear water from mud water. So mud, just sandy, that is insoluble. Then we are looking at insoluble from soluble, from a liquid. So question A, name the process that a learner would use to obtain the clear water. So here we can just use filtration. So filtration can be used here. Draw a large label diagram to show the arrangement of the apparatus the learner would use. So under filtration, we can first begin with draw the beaker where the pure water would be collected. Then from there, we need to use a funnel. Then what else are we supposed to put? We need to use a funnel paper. So we need to use a funnel paper. So we put a funnel paper somewhere here. Okay, so then from there we get we can call it maybe a beaker where there is the liquid that we want to, the mixture. So here we have mixture of water and mud. Then here we are expecting, then the mud will remain here since these are in large particles and in solid state, so these will be considered as residue. Then what are we going to have? So we are going to have the filtrate, which is the water that we want, will be collected here. So we have our filtrate, then we have funnel, then we have filter paper. So this is it that we can draw. We'll move on to question C. Give an industrial application of the process named in A1 in A above So in industrial application, we can just say purification of water. Purification of water. So companies that deals with water, they need to purify by using filtration. It's used there. Then we move on to question 5. Chlorine, bromine, and iodine are elements in group 7 of the periodic table. A1, describe the change in the states of the elements at room temperature and pressure as the atomic number increases. So we are looking at the states of matter. So say the states of matter changes from gas to liquid and from liquid to solid. Then why is chlorine used in water treatment? So say because it is poisonous, so it is able to kill the microorganisms that we consider as unwanted. Right, then what happens? We go to question B. Write an ionic equation for the reaction between chlorine and aqueous potassium bromide solution. So first, let's write our word equation. We'll begin with word equation. So we'll begin by potassium bromide plus C chlorine. So the first step is we need to check if this reaction will take place. So let's look at the arrangement of these elements in group 7. So the first one, the one on top, is fluorine, followed by Cl. Then we have bromine. From there we have iodine. So let's just end at iodine. Then according to the reactivity of group 7 elements is that as you move up the group, their reactivity increases. So the one on top is more reactive than the one below. So if you look at chlorine is more reactive than bromine, so it can displace bromide from the compound of potassium bromide. So here we are going to have potassium. So we'll say potassium chloride, then plus bromine, since it is displaced. So this is a single displacement. Then the chemical formula for potassium bromide is KBr aqueous plus chlorine. It's the atomic, it's a gas at RTP. Then the potassium chloride is also aqueous plus bromine, which is the atomic. Then what are we supposed to do? We just have to balance our equation. So we can just put a 2 here. Also, we put a 2 here. So our equation is balanced. So this is the chemical equation, but we need ionic. So let's convert the compounds that are in aqueous stage, phase, into ions. So the first one is potassium plus aqueous, then bromide minus aqueous, then chlorine must be just written like this since it's in gaseous state. So we have potassium aqueous plus 2Cl. Let me just put a 2. So this number is affecting the 2 involved, plus the bromine will be written like this. Okay, then what are we going to do? We have the overall ionic equation. So what we just have to do here, we just need to cancel the spectator ions. So ions that have the same state, which is aqueous state, on both sides of the equation. So potassium is a spectator, then the rest are those that are. So our final answer is 2Br minus aqueous plus chlorine, then giving us 2Cl minus plus this one. And if you look at this equation, this is also a redox reaction, because we can see the change of oxidation numbers, but let's not focus into that. We move on to question 6. Below are chemical formulae of organic compounds: C2H4, CH3OH, CH3CH2, COOH, HCOOH, C2H6, CH3, COCH2OH. So these are organic compounds. Then we have to know the families from where these organic compounds are coming from. Alright, so the first one, if you look at this one and this one, so one is an alkene, then the other one is an alkane. So the one with more hydrogen is an alkane. Then the one with less hydrogen, since the number of carbons are the same, this is an alkene. Then the presence of OH indicates alcohol, so remember that. Then here the presence of Cu, so CO2H can be written as COOH. So this is a functional group for carboxylic acid. So this is an acid, this is an acid. Then we have an alcohol. We have also here an alcohol. We have alkane, alkene. Okay. Then question A, name the compounds which react with steam. So the reaction of steam with an organic compound is known as hydration, and hydration forms the alcohol. Then a family that can only undergo hydration is the one with ENA, which is, we just say C2H4, which is, this is ethene. So whenever ethene react with steam, we get ethanol. Then number B, draw the structure formula of a compound which turns blue litmus paper red. So this is same as we want to draw the structure of any acid. Remember, there are about 2 acids, so we can draw any of the 2. So let's go with this one. So we have CH3. So the 3 atoms of hydrogen will be here, these 3 here. Then we have 2 atoms of hydrogen here. Then we have the Cu. So the Cu will have double bond here, then OH. So this is the structure of a carboxylic acid. Then C, choose 2 compounds which are isomers. So isomers having the same chemical formula but different structure formula. So we need to look at 2 compounds that we can see that the formula must be the same. Now, how can we handle a question like this one? So we just have to count the number of carbons and hydrogen atoms in each. If they found to have the same and exactly, then those can be qualified as the isomers. So from this, and without wasting much of our time, these can work as isomers. So let's see how we can consider this one as isomers. So we have CH3, CH2, CO2H. Then we have CH3, CO, CH2OH. So let me count the number of carbons for this one. So we have 1, 2, 3. So there are 3 atoms of carbon. What of hydrogen? We have 3 plus here 5 plus here 6. So CH3H6. Then let's check for the second one. So 1, 2, 3. Okay. Then 3, 5, 6. So we can see that the molecular formula are the same. So they have equal number of carbons and hydrogen atoms. So these two can qualify to be isomers. So we just say CH3, CH2, CO2H, and CH3, CO, CH2OH. We move on to D. Which two compounds can undergo esterification? So esterification is a reaction between alcohol and acid. So we just have to choose two reagents. One must be an alcohol, then the other one must be an acid. So we can even use the same that we've indicated here. So CH3, CH2, CO2. So this is an acid. And CH3, COCH2OH. Then this is our alcohol since there is OH. So that's what we can see. Then for question 7, we have a solution of aqueous sodium hydroxide was added from a burette. So this one is coming from a burette. So this one is considered to be a titrant. So it's a titrant, and a titrant has a known concentration. Then burette to 25.0 cubic centimeters of dilute sulfuric acid solution in a conical flask. The pH of the mixture was measured during the addition of sodium hydroxide. Describe how the pH value changed. So the pH before the addition of sodium was indicating the acid, because the acid was the one that was in a conical flask, and in a conical flask is where we put the indicator. So the pH now, after the titrant was added, then the pH started to change from the acidic medium into the neutral medium, since we are forming a neutral solution, which is salty and water. This is a neutralization reaction because we are dealing with a strong base and a strong acid. So here we'll say the pH changed from acidic medium to neutral, and the neutral point is always considered as the end point of the reaction. B1, name the type of reaction that took place between sodium hydroxide and the sulfuric acid. So sodium hydroxide is a strong base because sodium is very reactive. Sulfuric acid is also a strong acid. So the reaction between a strong base and a strong acid gives us a neutral substance. So the reaction is neutralization, is what we can put here. Write a balanced chemical equation for the reaction above. So the first one, the chemical formula for sodium hydroxide is NaOH. It is in aqueous phase, plus C, sulfuric acid is H2SO4. Remember, the sulfate is a radical with a valence of 2, sodium with a valence of 1. So if we interchange, it will give us sodium Na2SO4 in aqueous, plus C. What are we getting? The hydroxide will react with hydrogen, giving us H2O, which is water. So what are we supposed to do here? We can put the 2 in front of sodium hydroxide so that we can have 2 atoms of sodium on the reactant as well on the products. What else are we supposed to look at? Look at hydrogen. From the sodium hydroxide, 2 atoms of hydrogen and 2 atoms of hydrogen from the sulfate. So in total, we have 4 atoms of hydrogen on the reactant side. So we put a 2 here. So that 2 times these 2, we have 4. So our equation is now balanced. Question C, sulfuric acid is a strong acid. What does this mean? So say it ionizes completely when dissolves in water. Okay, we move on to question 8. Define the term concentration. So say this is, so say the number of moles of solute per cubic decimeter of volume. Then question B, calculate the concentration of the solution made by dissolving 60 grams of sodium hydroxide NOH per less in 300 cubic centimeters of water. So concentration is given by this formula. Concentration is equal to number of moles over volume. Now we don't have the number of moles, we have mass. So we can find the number of moles by mass. So say number of moles is given by mass divided by molar mass. So there is a need of finding molar mass for sodium hydroxide. So let's do as wise. Right, so Mr is equal to, we have 1 atom of sodium, so Na multiplied by 1, O times 1 plus hydrogen times 1. The mass number for sodium is 23 multiplied by 1, 16 times 1, 1 times 1. 23 times 1 is 23, 16 plus 1. So the sum is 40. So say number of moles is equal to, we have here, we can put 40 divided by, not 40, the mass is 60. So 60 divided by 40. So this should be 1.5. 60 divided by 40, getting 1.5 moles. So this is what we are going to substitute here. So say number of moles is equal to 1.5 moles over now volume. Remember, the volume should be in decimeter cubed, and we know 1 decimeter cubed is equal to 1000 centimeters cubed. So to convert from decimeter to centimeter, you multiply by 100, then the reverse, you divide by not 100 but 1000. So to change from cubic to decimeter, we divide by 1000. This will give us 0.3 decimeters cubed. So 1.5 divided by 0.3, I'm getting 5 moles per decimeter cubed. Or if what we can say concentration is equal to number of moles divided by volume. So concentration, where there is any, we can substitute with this formula if we want to do it at once. So this will give us mass over molar mass. So this is over 1. Let's change this operator into multiplication. So this will be 1 over V. So if we want to do it at once, this will be mass over molar mass times the volume. And if the volume is given in cubic centimeters, you want to do it without the conversion, then this number on top must be multiplied by 1000. So let's check. So remember, the mass is 60 times 1000 over the molar mass is 40 times the volume. Now the actual given is 300, so let's do math here. So 60 times 1000 is 60,000 over here we are going to get 12,000. So 60,000 divided by 12,000. So I'm getting 5. So it seems the same answer. So you can use any of those formulae. Question C. What is the effect of increasing the concentration of the reactants on the rate of the chemical reaction? So the rate would increase because the increase in concentration results in the increase in a reaction. So the rate would increase. Go to question 9, the last one. Draw diagrams to show the arrangement of particles. In the first one, aluminium. So aluminium is what? Solid. And we are told to show particles. In a solid, we know that the particles are closely packed. So this is what they want here. So this is what they want. Let me just draw big particles so that I don't have to consume a lot of time here. So the concept is you just have to draw a solid. But when drawing, just use the size circles. The reason why I'm using bigger circles, I don't want to use a lot of time on this question. So this is what they want since it's a metal. Now for hydrogen chloride has a chemical formula of HCl. Hydrochloric acid has the chemical formula of HCl. Now the difference is hydrogen chloride is in a gaseous state. Then hydrochloric acid is in a aqueous phase. So we want the hydrogen chloride which is in gaseous state. So here we can just use the principle under gases where the particles must be sparsely packed. Which of the two compounds has the lowest point? Give a reason for answer. So it is hydrogen chloride. Then reason because it is made up of covalent bond. So it's a covalent compound, and covalent compounds have lower melting point. So this is what we can discuss over this video. Thanks for watching.